Hello everyone, welcome to 7 course of the optimizationcity.com, where we will explore the concept of the minimum spamming tree. In this course, we will go into the idea of defining the most efficient way to connect the setup point while minimizing the total cost or distance. What we cover in this course in 4 sections. In this course, we will cover important topic related to the graph optimization. We start by introducing the minimum cost flow problem, explaining its basic and why it matter in the different area. Second, we explore the concept of the minimum spamming tree, discussing their feature, practical use, and how they help solve the connectivity issue. Then we go into the algorithm views for finding the minimum spamming tree. Finally, we do some example. In the minimum cost flow problem, we want to distribute the same type of product from the factory here to sell market efficiently. We know the quantity of product produced at each factory here 20 and the required quantity at each destination 5 and 15. Instead of sending the product directly to the destination, we can send them to the distribution center here, point 2 and point 3, through the intermediate point if needed. However, there are limits on how much can be transported on each transportation line. Here we have 4 for transporting the good from 2 to 4. The objective is to minimize the cost of transportation of product using while meeting the demand. $2 is the transportation cost per unit of transport. Look at the simple example here of minimum cost for a problem using the diagram here. The nodes are shown as a number seeker and the arc are represented by arrow. The arc have a specific direction, meaning the material good can be transported from one node to another in that direction. For instance, we can send the material from node 1 to 2, but we cannot send them from node 2 to node 1. We use the notation I-J to indicate that the arc going from node I to J here. In the figure here, each arrow represents the path with a specific capacity and cost for transportation. The capacity indicates the maximum amount that can be transported along that path, while the cost per unit represent the expenses associated with each unit of transportation. For instance, for arrow 2 to 4, the flow can range from 0 to 4. The first component of the parenthesis is a capacity. And each unit passing through this path costs $2. The symbol infinity here indicates that there is no limit on the capacity of the particular path. Moreover, the number in the parentheses next to the circle represents the available supply and the required demand at each node. In this figure, node 1 is a starting point with a supply of 20. Node 4 and node 5 are destinations that require 5 and 15 units respectively, indicated by negative sign. In the minimum cost flow problem, our objective is to discover the flow pattern that incur the lowest cost. To formulate this problem as a linear programming, we need to define the variable. Xij represent as a variable that the quantity of the unit transport from node I to J using arcij. Now let's represent the linear programming for minimum cost for a problem. We are going to minimize the objective function subject to a list of constraints. Equation 1 to 5 represent the flow balance equation in the network. Let's consider the flow balance for node 1. The equation states that the combined flow leaving node 1, which is x arc 1, 2, and 1, 3 as the x1 and x1, 3 should be equal to available supply at node 1, which is 20. This ensures that the outgoing flow match the available supply. Similarly, the balance equation at node 2 here indicate that the incoming flow to node 2, which is arc 1, 2, is equal to outgoing flow from node 2, which is arc 2, 4, 2, 5, and 2, 3. This ensures that the flow entering and leaving node is properly balanced as equation number 2. The minimum cost flow the minimum cost flow model in the network has a unique structure that helps to determine the solution algorithm. The flow available denote xij in the balance equation have the coefficient of 0, for example here, 0, +1, and -1. Additionally, this variable appear precisely in two balance equations. Once with the coefficient of the +1 representing node where the flow originates, for example, x1, 2, 1, node 1 is the origin of the arc 1, 2, and the ones with the coefficient of the minus representing the node where the flow enter. For example, here node 2 is the end point of the arc 1, 2. Based on the above characteristics, the general form of the minimum cost flow problem can be expressed as follows. This model shown here represents the general form of the minimum cost flow problem. However, we can simplify this model into the other form, which is explained here. The minimum spanning tree involves connecting the different nodes in the network in such a way that the shortest distance is established. The connection between nodes are not directional. Here, there are some examples of how this problem can be applied in the real world. In first one, the company need to minimize the amount of electric cable used to provide electricity to various points in the building using the minimum spanning tree. The second one, the Ministry of Road is seeking the most efficient way to connect the village in the same region, minimizing the list of the connecting paths. And the last one, this Water and Sewage Department aim to create water supply network in a town under construction using the shortest possible length of pipe here. So let's go to the algorithm of the minimum spanning tree. The algorithm for finding a minimum spanning tree can be explained using the simple word as follows. In step 1, create a square matrix of size n times n, representing the distance between n point or node numbered from 1 to n. In step 2, start from any point and find the shortest distance between that point and the other point. To do this, extract the row corresponding to the selected point from the matrix and create a 1 times n matrix. Choose the smallest number in the matrix as the shortest path. Consider this point as a second point. We go to the next step as a step 3. We repeat the process in step 2, but now consider the 2 points selected so far, which is node 1 and 2. Create a 2 times n matrix based on these 2 points and select the smallest number in the matrix at the third point. Continue this process until all points are selected. In the step 4, which is the last one, the order in which the points are obtained represent the optimal sequence of the connecting them in the tree. The sum of the distance in this tree will be the minimum possible distance to connect all points. There is a note we should consider. If there are 2 or more equal number in the matrix at any stage, there may be a multiple solution of the algorithm. Consider an example. In a building, there are 6 points that need to electrical wiring. The distance between these points are given in this matrix. The symbol infinity here represents the impossibility of the wiring between 2 points, By applying the minimum spanning tree algorithm, we can find the minimum wire in tree and determine the minimum amount of wire needed for connection for 6 points. In the first step, k is equal to 1, we need to choose the point arbitrary. Let's choose point 1, although any other point could be chosen. We create 1 times 6 matrix for this point as a follow. In this matrix, the smallest number is equal to 1, which is marked with a square around it. This number represents the distance between point 1 to 2, indicating that the shortest distance to point 2 has been founded is equal to 1. In the second stage, which is called is equal to 2, we add point 2, which had the shortest distance in the previous step, to the 1 times 6 matrix, and we now have a 2 times 6 matrix. Note that since points 1 and 2 has been assigned, we mark column 1 and 2 with the dash symbol, indicating that there is no need to check this point value. In this matrix, the smallest number is equal to 3, which represent the distance between point 2 to point 5. Therefore, we also have the shortest distance to point 5. So in the next step, which is k is equal to 3, we expand the matrix by adding row number 5. This results in a new 3 times 6 matrix. In the fourth step, we identify the smallest value in the matrix, which is equal to 4. This number represents the distance between point 2 and 4, okay? And we continue to performing the same step for the next iteration. So we add the row number 4 in the step number 4. And minimum value of this matrix is equal to 3. So in the next iteration, we had to add row number 6. So this is a step 5. And this is the final matrix. In this step, we observe that there are 3 numbers equal to 5, which are the smallest number in this matrix. As a result, the problem has a 3 solution. Since the shortest distance to all points has been obtained, so the algorithm concludes. The figure here shows the 3 solutions to the problem, which represent the minimum spanning tree for the example. And the length of the minimum spanning tree for these 3 solutions is equal to 16. Let's solve another example. Find the minimum spanning tree using the given distance matrix. So in the solution, we start by choosing node number 6 as our arbitrary starting point. The arc 6, 4 is selected with the smallest value is equal to 4. Next, we select node 1 and 2 in the same time and in the same iteration, add arc 4, 1 and 4, 2 to the tree with the smallest value in the next iteration. Then we choose node number 5, because the smallest value in this matrix is equal to 5, and add arc 2, 5 to the tree with the lowest cost. Finally, we select the node number 3 because the 5 has a minimum value in this matrix. So the minimum, and this is the final table, and you can see that the minimum spanning tree, because we have a one unique solution here, only 1, 5, we have one solution, not multiple solution like the last example. So this is the minimum spanning tree for the problem, and the length of the minimum spanning tree is equal to 20. Thank you so much for watching. If you want more practice to improve what you have learned, I've got something perfect for you. Check out my website, optimizationcity.com, where you will find plenty of exercise to explore more about the minimum spamming tree, also another topics in operation research. Okay, thank you so much again for watching us. Or if you have any question, you can send an email by optimizationcity@gmail.com, or you can fill out the contact form in our website, where optimizationcity.com. Goodbye for now.